Friends, let us do a very interesting problem on applied psychrometry. This is extremely relevant problem, relevant in the sense that it would help you appreciate the practical design procedure of AC system. We would be doing this design for a hot and humid climate, and by design, I mean we would be selecting the cooling coil capacity. Along with that cooling coil capacity, we would also estimate how much should be the mass flow rate and volume flow rate to be supplied to the space to be conditioned. So the conditioning is for a typical classroom, which is shown over here. This is the classroom. Okay, and for this classroom, load calculations have already been done, and the sensible heat and the latent heat has already been determined. So the problem statement looks like this, that after load calculations, the sensible heat component is 18 kilowatts, the latent load is about 7 kilowatt, and because this is the lecture hall, it requires ventilation. Ventilation means fresh air needs to be supplied, and that requirement is 10 liters per second for 1%, and hence for the total 120 students, let us say it would be 1200 liters per second. Okay, so 1 liter is 1000 cc, or 1 liter is 10⁻³ meter cube. Okay, so with this understanding, we would know the amount of ventilation is already known, and we would be designing the AC system. So for designing the AC system, we need to first design or state the indoor design conditions, and we need to state the outdoor design conditions. This is the first step in any design. So let us say that in this classroom, we are maintaining a temperature of 24 degree centigrade and RH of 50%. Okay, so this is inside design conditions. So 50% is the relative humidity and 24 degree centigrade is the dry bulb temperature we want to maintain. And for the weather conditions of Nasik, which is in tropical part of Asia, the climatic conditions are taken to be 36 degrees centigrade as a dry bulb, and 60% is the RH which is taken. So this I am already defining initially, or I am assuming this outside design conditions. So the design starts with defining the indoor conditions. Let us say I, or you can call it as R for room conditions, and outdoor design conditions by the alphabet O. Okay, so what you can do is that you can plot this on the psychrometric chart as the first step of your calculations. So on a psychrometric chart, you can plot 24 degrees centigrade and 50% RH. So this is your inside design conditions, and suppose this is your 60% RH line, and this is your 36 degrees centigrade. So this becomes your outside design conditions. Okay, so this way you first identify the inside design conditions and outside design conditions on the psychrometric chart. The next step is, because you already know the sensible load and you know the latent load, so you calculate the room sensible heat factor. So room sensible heat factor is nothing but the ratio of the sensible heat upon the total heat. Total heat is the sensible heat plus the latent heat. So sensible heat is given to be 18 kilowatts, the latent heat is given to be 7 kilowatt. So 18 upon 18 plus 7, that gives us the room sensible heat factor of 0.72. So what we need to do is that once you get this room sensible heat factor line, room sensible heat factor value, you can plot it on the psychrometric chart. So on the psychrometric chart, you will find that there is a sensible heat factor scale over here. Sensible heat factor scale over here. So on that, you are supposed to look at that 0.72. The next step is to start with, we can assume the supply air conditions. Okay, because this is the assumption that we are not given any information about the bypass factor. Okay, and we are not told to calculate the ADP. So what we will do is that, because we want to maintain the room at 24 degrees centigrade, okay, then we can think of some temperature which would give you sufficient delta T. So let us say that supply temperature is 14 degree centigrade. Okay, the other way of doing it is you can find the ADP, that we will do in the next problem. Okay, but here we are assuming the supply temperature to be 14 degrees centigrade for simplicity as a first step, because it's the first problem we are solving. So supply temperature is 14 degrees centigrade and the room temperature to be maintained is 24 degrees centigrade. It means that the delta T, okay, is 24 minus 14, which is 10 degrees centigrade. So now let's look at this, that you have the room sensible heat factor, which is I, and you have plotted O. You have also calculated the sensible heat factor 0.72, right? Now you need to be sure about what is the quantity of air which needs to be supplied to the AC apparatus. So let us try to understand the physical system first. That's this is your room or classroom or lecture hall to be maintained at 24 degrees centigrade, and you are supplying the conditioned air at a temperature Ts. This conditioned air comes from the apparatus, which is your cooling coil, and this cooling coil is supplied the air, which is a mixture of the fresh air and the recirculated air. So what you are doing is, the cooling coil is receiving mixed air. Okay, how is it mixed? Because the room air is returned back to this cooling coil and some of the fresh air is introduced. So this fresh air which is introduced, it is called as ventilation air, and it is given that this ventilation air in our case is already defined, and that is given to be 10 liters per person, or it is 1200 liters for 120 students. Okay, so this is already given, 1200 liters per second is to be supplied. This is your fresh air volume. Okay, fresh air volume is given. Now first what we will do is that we will find out how much is this quantity of air to be supplied. Okay, and how much is this quantity of air to be supplied. So for these calculations, it's very simple. What you do is that you take the total load. So the total load on this classroom is the summation of sensible load and the summation of latent load. Sensible load was taken as 18 and the latent load was taken as 7. So 18 plus 7 is 25. Okay. So 25 into M into HR minus HS. This is one way of doing it, or this is total load. Or what you do is that you take only the sensible component QS is equal to M dot into CP TR minus TS. Both these are correct because here we are only writing the formula for sensible heat, and here we are writing the formula for total heat. So both these expressions is going will give you the same result. So let us say that I am doing by this method. So sensible heat is 18 kilowatts. M dot is to be found. Cp of here is standard value 1.02. The room temperature is assumed to be 24, and the supply temperature is assumed to be 14. So this gives me a delta T of 10 degrees centigrade. Okay, and you can find out the mass flow rate. So this is one simple method for finding the mass flow rate. Or the other method is you find the enthalpy HR, that is the room air enthalpy, or HI, and you find the supply air enthalpy from the psychrometric chart. So psychrometric chart, you have inside design conditions, you can read the enthalpy here HI, and you have the supply condition, okay, yes, on the room sensible effector line. Okay, so there you can find the corresponding enthalpy HS. Okay, so these two ways you can do the calculations and find the mass flow rate. So the mass flow rate calculated is 1.76 kg per second. Now this mass flow rate is going to offset the room sensible load. Okay, so this room now you are supplying the mass flow rate of 1.76. Okay, it means you are supplying a volume of mass into specific volume. Specific volume is about 0.8, mass is 1.76, so that comes out to be around 1.47. Okay, or you can divide it by density. Multiplying by specific volume is same as dividing by density. So the volume to be supplied here, this is mass, right? Mass is 1.76 kg per second, which is nothing but equivalent to a volume of 1.47 meter cube per second. Or if you want, you can express it in per hour by multiplying this with 3600. So if you multiply this with 3600, you will get the volume as 5290 meter cube per hour. Right? So what we have calculated now is how much is the amount of air to be supplied to the room. Right? But amount of air to be supplied to the room is not the same as the amount of air which is returned, right? Because some of the air is returned and some of the air is fresh air. Now, as we had said that the fresh air requirement is already given because there are 120 occupants or 120 students in the class, and each requires, let us say, 10 liters per second. So about 1200 liters per second or 1.2 meter cube per second is your ventilation requirement. So you see that the ventilation requirement is huge in this case, and the total supplied quantity is 1.47, means about 82% is the fresh air to be supplied. This is in this unique problem, and only the remaining part, that is about 18% is to be returned back. Okay, so in this case, now in this problem, you will find that this room major quantity is your fresh air, which is 82%, and only 18% is retained. 18% is retained, and remaining 82%, that is 0.82, is thrown off. Okay, so this is the arrangement here, right? So this is a very high ventilation application. So now you need to find the enthalpy of the mixture, because you have the fresh air coming and you have the return air coming, and these two are mixed. They are mixed, and this mixture is supplied to the cooling coil. This mixture is supplied to the cooling coil. So you want to find this. Okay, so how much is fresh air? Fresh air in this case is 0.82. So its enthalpy is, let us say, H naught, and return air in this case is 0.18. So you can find the enthalpy of this return air from the psychrometric chart. So how do you find this? So on the psychrometric chart, you have already plotted the value of, plotted the point O, okay, and you have already plotted the point I. So you can read the corresponding enthalpy on the psychrometric chart HO, and you can read the enthalpy HI, and you can find the state M. Okay, this M can be found out, right? So how to find this M? By energy balance. So HM is equal to 0.82% of outside air and 0.18% of return air. I use HI here, but you can also use HR, room air. Okay, so if you do this calculation, you get an enthalpy of 73 plus 8.46, which is 82.3 enthalpy. Okay, so once you get this enthalpy, you can locate the point M. Okay, or you can, what you can do is that you can also estimate the temperature of the mixture as like this. Temperature of mixture is equal to 0.82 temperature of outside air plus 0.18 temperature of room air inside air. Okay, this will also give you the temperature and the point M on the psychrometric chart. So if you read the temperature here Tm, you can join this line and get the point M on the psychrometric chart. So this is how you find the mixed air enthalpy. So once you get the mixed air enthalpy, now finding the cooling capacity is very simple, because now what you have is the HF value, which is 82.3. What you require is the supply air value. Okay, so on the psychrometric chart, suppose this is your I, this is your O, and this is your M, and this is your conditioning line. Okay, so from this conditioning line, this is your ADP. Okay, and so this is your supply condition, yes. So supply condition, yes, you want the enthalpy, right? So for finding this enthalpy, we have taken the supply air temperature as 14 degrees centigrade. Okay, 14 degrees centigrade. So supply air temperature as 14 degrees centigrade if you take, right, and you are basically having the enthalpy from the psychrometric chart at this point, which is 82.3. So if you take 82.3 and if you have the enthalpy, you would get the supply air enthalpy as 34 kilojoules per kg. Okay, so how you get that? So you can just read this value at 14 degrees centigrade ADP as 34 kilojoules per kg. Okay, now mind well, what we are doing is we are slightly simplifying the calculations. I will just repeat this because that might create a confusion in your minds. See, what we have done is, as a simplification, we have already assumed the supply state conditions. Okay, so supply state conditions were assumed, right? And we have the points O and we have the points I. So actually what we do is, and this is your yum, okay, and you already have calculated the sensible heat factor. Okay, so the actual procedure is you draw the sensible heat factor line, okay, corresponding to your 0.75 or whatever you have got earlier, and that intersects at the saturation curve TADP, and that value is approximately 14 degree centigrade. Okay, but here we are already given that 14 degree centigrade. Okay, so if you read the corresponding enthalpy here, that comes out to be 34 kilojoule per kg, right? So 34 kilojoule per kg is the enthalpy here, and we know the enthalpy at point M, which is around 82.3, 82.3, right? So the difference in this enthalpy into mass flow rate is the cooling capacity. So you know this enthalpy and you know this enthalpy, right? So for the cooling coil now, so this is the cooling coil. It is receiving the air at the state M, whose enthalpy is 82.3, and it is conditioning it up to a supply state which is 14 degrees centigrade and whose enthalpy is 34 kilojoule per kg. Okay, so state M means mixed state rather than. So mixed state enthalpy is 82.3 and the outlet enthalpy is 34 kilojoule per kg. So the difference in these two enthalpies into the mass flow rate, okay, which is 1.76, that gives you the cooling load, and if you multiply this two, you will get a cooling load of 85 kilowatts, which is approximately 85.15. If you divide this two, you will get TR of refrigeration. So this is how we do the design calculation. So what we had done is, first we had calculated RSHF. Okay, from RSHF you determine actually TADP, right? Because the bypass factor is assumed to be 0. Then what you do is that you get the mass flow rate by either room sensible heat upon Cp delta T or room total heat upon delta H, right? And once you get mass flow rate, you estimate basically the mixture condition, because here it is the ventilation plus the room load, and that mixture condition, once you get the temperature of the mixture and enthalpy of the mixture, you get the coil load or coil capacity. So this is the procedure. Okay, so this way we had calculated the cooling coil load or cooling coil capacity in our first problem. So let me repeat what is the first problem. The first problem is, here we are assuming that the bypass factor is 0, okay, and we are designing a coil for a, for for an application which is a classroom having 120 students whose sensible load is 18 kilowatt and latent load is 7 kilowatt. I hope that you have understood this. Here the special case is ventilation load is significantly high because it is a closed room and there are many students in the classroom. Okay, so that is the reason why the ventilation load is high, and that changes the entire calculation also.